Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but a lot of the same principles apply over in the UK as well. Now, if you have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring that. And if you're watching this after the premiere, then just feel free to leave a comment underneath the video, and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on Diagnostics technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had a group of about 30 different franchisees I worked with, as well as the shops that they service, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru, so I worked in a dealership, and over time, I guess, I just became that default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that had come into my bay. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. Our topic at hand is going to be light duty diesel diagnostics. I didn't want everyone to think we're working on big rigs tonight. We're going to talk about things like Ford F-350s and Ram trucks and Sprinter vans and things like that. And I know some of you, probably a decent amount of you, maybe don't work on diesels. Maybe you work on gasoline engines instead. So this will kind of hopefully help out with that, a little bit more understanding as to how they work. So they are similar in many ways. Many of the sensors are going to be the same, but many ways they're different. So one of the things, they both need the same four ingredients to run, by the way. Air, fuel, compression, and an ignition source. So that's going to be common across both of them, but how they do it, how they go about it, of course, is going to be a little bit different too. The fuel is going to be different. So gasoline is a petroleum-based product that is more refined than diesel is. It also has less energy available during combustion, and its auto ignition temperature is higher than diesel, about 475 degrees Fahrenheit. Diesel is also a petroleum product. It's not as well refined as gasoline, so it goes through fewer refining steps. It does have more energy available during combustion, and its auto ignition point is lower than gasoline at 410 degrees Fahrenheit. So the way they use compression is different as well. So gasoline engines compress the fuel and the air mixture before igniting it with a spark. Now, compression in a gasoline engine is generally around 100 to 150 psi per cylinder, versus on a diesel engine, they use that compression to compress the air charge before fuel is mixed in. So it gets superheated air in there, and then it squirts the fuel in there, and it hits the auto ignition temperature, and it ignites. Compression in a diesel engine can be 500 psi or more per cylinder, just because of the way the cylinder heads are designed. So, for example, as we know in a gasoline engine, we have a large, decently large combustion chamber in the cylinder head. Piston goes up, compresses the air and fuel, and then we light it with a spark. Versus on a diesel, the piston is the combustion chamber, basically. So it goes almost flat to the head, and then it just sprays the fuel into the piston, and because of the superheated air in there, it goes in there, right? So by design of that, though, can create NOx emissions, can run kind of lean. So we have ways of controlling that we're going to talk about a little bit later. The first part, though, we're going to talk about the fueling system, because that's one of the major differences between them. And you know what? The lines are blurring a lot now. So with gasoline direct injection engines, a lot of these principles and a lot of these setups are going to be very similar between a diesel and gasoline, because many diesel engines are going to be direct injected. So, for example, this common rail injection that they would use on the Duramax, on the GM, and also the Dodge 5.9 and 6.7, they also use common rail injection. And these are going to be more your fairly standard poppet style. Injectors. There we go. Uses high pressure fuel provided by a camshaft driven pump. So it has a lift pump that increases the pressure. It's driven off the engine. And of course, the injectors are electronically controlled. Each unit injector has electrical connector and high pressure fuel at it. So it's going to look kind of like this. So we have our fuel tank, and then it goes into the higher pressure pump. And the higher pressure pump increases the pressure, of course. So then it goes through this common rail, and then the cycles through and then goes through the injectors and sprays out. And then of course there's a feed back into the tank if necessary. The electronic control unit controls it all just like it would on a gasoline engine, right? We got cam sensors, crank sensors, etc. All the same basic types of sensors that control it. It's just how it's set up with the common rail. With the very high pressure, it could be up to 30,000 psi. You need to make sure, if anytime you're working on this, you want to make sure it is depressurized. Don't tap into the fuel rail. Anytime you crack into the connection, the entire rail has to be replaced. So we don't want to do that. The fitting compresses one time, and that's it. And it is a necessity to replace everything, since the high pressure rail and the high pressure fuel coming out. You ever seen a water jet? Same type of principle, right? So it's very, very high pressure, and it can cut off digits and so on. So you don't want to mess around with that. Ford, on the older Fords, they use what they call hydraulic electronic unit injection. So what this does is it uses high pressure motor oil to magnify the fuel pressures. So the fuel going in is only your standard, maybe gasoline level, 45 to 65 psi. And then they use high pressure oil inside the injector in order to increase the amount of pressure on the fuel coming out the other end. So this is kind of how they got around it, right? So the main components of the injector assembly are going to be the solenoid at the top, which is going to open and close this guy. We have the oil chamber in here, which the oil will flow through. Poppet valves, which is going to open and close. Intensifier piston, which is going to increase the amount of pressure on the fuel. Fuel chamber in here, and then the nozzle down here at the end. So the solenoid will open up the oil chamber, allow that high pressure oil to flow in. So we have O-rings around here, and the oil flows in from the side. Oil is going to flow in. It's going to kind of push up on this, and then it's going to push down on this piston. As it pushes down on the piston, there's going to be fuel down here on the bottom part. And as that fuel goes in here, the pressure is going to increase because we have a large surface area there and a small surface area there due to multiplication of forces. It is going to take that force and multiply it and bring it down here and increase the pressure of the fuel. Once that fuel pressure is able to overcome the spring tension here, it will push the nozzle back and it will start spraying fuel. And that's how that works. Right, so there we go. Now the newer Ford engines, 6.4 and 6.7, they also went to a high pressure common fuel rail, but they use a different type of injector. And I'm sure some other engines use this injector too. We see these a lot in the gasoline direct injection engines. There we go. So each injector has an electrical connector, high pressure fuel, 26,000 psi or so, and piezoelectric coils. So that's a slightly different working injector. So it's going to look kind of like this. They're fairly long, and they go like right in the center of the cylinder head. They have the piezoelectric activator, which is in here. We have stroke amplification in here that's going to work on a similar principle to those hydraulic units, where it's a small stroke on one side, bigger stroke on the other side due to multiplication. Hydraulic control in the middle, or kind of towards the end, and then we have fuel atomization down the very end by the nozzle. So if we were to take a look at the piezoelectric actuator, we have a piezoelectric stack, which is going to be these thin wafers. Now, if you know how a knock sensor works, and maybe you do or maybe you don't, but how a knock sensor works is that when it vibrates, so that when it has motion applied to it, it generates an electrical current. So we can do the same thing in reverse. We put an electrical current going in, it's going to make it move. So instead of taking mechanical motion and turning electricity, it takes electricity and turns it into mechanical motion. So we apply electricity, they go out. Take the electricity away, they come back in. So by doing this, we can make them move. Now it's a very small movement, so we need to be able to amplify that movement. So we have this amplification chamber here, right there. And when no fuel is in here, it's just going to kind of sit there and go back and forth on the spring there, and nothing really happens. Once fuel is in there, however, we can then hydraulically couple these two pieces together, and it's going to change the stroke length. So I have a small amount of stroke going in, large amount of stroke going out. So it pushes, and it pushes the other end because we have the diesel fuel in the middle. Right? So it intensifies it, just like on those hydraulic units. So we have high pressure fuel going in, and that increases the stroke. So we have the high pressure fuel going in here into the system, and then it kind of goes around and that pushes down on the pintle to keep it closed. When we remove that, however, by moving the stroke and moving it back, relieving the pressure that's in there, holding it closed, it allows the fuel to get around and allows it to spray. So it's going to look something like this. Right, fuel holds it closed. When we relieve that fuel, it's going to do this, and then is going to open and spray. Just like that. So if I have high pressure fuel over here, once this opens and moves away, then we open the injector and spray. So it's really pushing the injector backwards, or pushing the nozzle backwards. It does that. All right. So with your scan tool, many diesels at this point need something done with the fuel injectors in order to, when you replace them, to get the flow rate correct, right? So injector quantity adjustment is one example on a Ford. So this is injector quantity adjustment. You're going to use a 10-digit code on top of the injector. Don't confuse characters like 8 and B, D and 0. On the next screen, it's going to show you the current codes, and then select the injector to be programmed. So it's going to, here's the codes that are in there, entered. I would just hit edit, and I would type them in, type in whatever the code is, and then hit OK, and then it would code that to the vehicle. Because every injector is going to flow a little bit differently, so I need to make sure the computer knows which injector it is. All right, so that's fuel injection related stuff. So that's one way it's different, but it's very similar if you think about it, right? In gasoline direct injection and diesel injection, it's going to work very similar, especially now. No ignition system, though. They do, however, have emission systems, and they are a bit more complex than on your gasoline-powered vehicle, because there's a lot more going on. There's a lot more stuff they need to take out of the exhaust. So post-combustion, they're going to take care of it with oxidation catalyst, the diesel particulate filter, and selective catalyst reduction system. That's an SCR. So here's just an example of a system on a vehicle. So we have turbo, which can be variable geometry. That helps with back pressure. We also have a dosing injector that would go in here. We have multiple temperature sensors and pressure sensors and NOx sensors. We have the oxidation catalyst. We have the DPF, which holds the soot. There's a differential pressure sensor that measures the in and the out to see whether or not it's clogged. We have NOx sensor, like I said. We have a DEF injector, which is diesel exhaust fluid, which goes into the selective catalyst reduction, which allows the chemical reaction to occur inside there, inside the catalyst. And then there's also an after catalyst as well, and that goes out the back. So what comes out the back should be a lot cleaner than what's going in. Also with the DEF, we have the tank, we have the heater, supply module, filters, all sorts of other ancillary things involved with it. So for exhaust after treatment, soot after treatment, we're going to talk about the oxidation catalyst, the diesel particulate filter, exhaust temp sensors, DPF back pressure sensors, and hydrocarbon dosing valve. And the main thing we're worried about in here is the diesel particulate filters, or DPFs. So it works just like the picture. There's little elves in there, and they take the soot and they collect it. Well, not really the elves, but collects soot, and then once the soot gets to a certain level, I'm going to start clogging this thing. So then the vehicle would then need to know, all right, I got to burn this off. Now, when I first heard about this years ago, I thought it was pretty wild that that this was a thing that they even said, yeah, let's do. Because what's it doing? So I'm driving down the road. Any of the soot that's in my exhaust gets collected in here. Then it gets filled up to a certain point. So I got a lot of soot in there. And then I'm going to burn it off. So I'm taking a lot of soot and dumping it in one place versus having just a little bit of soot in multiple places driving around, you know? I don't know. It seems like we're just kind of kicking the can down the road at that point, right? So storing up all these emissions, and then we just burn it out the back of the tailpipe when we do a regen. Right? So I don't know. But that's what they're doing. And also gasoline particulate filters are a thing now too. So we'll be seeing those more and more on gasoline engines, and it's the same type of principle. So inside those DPFs, there's opposing honeycombs, and they can flow through and collect in these honeycombs. But once it's full up, it's full up. And usually once it's full up, you're going to get a code. And usually also when it's full up, you're not going to be able to regen it. You're going to have to replace it. So that could be a problem, and a lack of maintenance could generate this problem. Speaking of regens, we have a few different conditions where we would regen and remove that diesel or the soot from the DPF. So when the DPF temps are high, a passive regen is when the DPF temps are high enough to burn the soot from the DPF without needing extra fuel. Only happens under high load situations, like going up a hill or something like that, or towing, I suppose. Active regen can be initiated by the PCM or by a scan tool. Extra fuel is going to then be added to the exhaust to raise DPF temps to approximately 1,025 degrees Fahrenheit to burn that off if it gets really hot. And then there's also a parked regen, which can be initiated by a dashboard switch. You can also, basically, it's the same thing as an active regen with a scan tool. It's going to be used when attempts of active regens fail. So the little switch that comes on, and then it just does it as it's parked. Now, with these systems, with the DPFs and the SCRs, they can be set up in different ways, different configurations. You can have DPF first, or you can have SCR first, or what have you. But we're going to be dealing with a lot of NOx, or a couple NOx sensors anyways, multiple exhaust gas temperature sensors. Hydrocarbon injector, that's what lights off the DPF and heats it up. DEF injector for the SCR system. There's a differential pressure sensor that goes in there in the middle. And that measures the pressure going into and out of the DPF, so it knows when it's clogged and when it needs to regen. And then, like I said, multiple exhaust gas temperature sensors and so on. So oftentimes, things like the NOx sensors anyways, might need to be reset or relearned on the vehicle. Could be the exhaust gas temperature sensors, could be the injectors. There's multiple functional tests that you might need to use for the DEF system. And differential pressure sensors is ways we can measure that too and test it. We'll see a lot of that in a little bit. So with those EGTs, there's multiple EGTs, as I said. So you're going to have one before it gets into the system, and then multiple along the way through the system, so it can measure temperatures, making sure that things are going as they should, making sure the temperatures are correct. So it should be cooler in. Then after I light the injector there, it's going to be a lot warmer over here. So I should see warmer over here. And I guess a little cooler over there on the other side after I've burned off the soot. So that's kind of how it works. You're able to see it. Now, the SCR system, which oftentimes is used in conjunction with the DPF, it's going to consist of your diesel exhaust fluid, which is 1/3 urea and 2/3 water. That's the blue jugs you see everywhere. Or if you're around, like where I live, there's a gas station down the street that has it right in the pump. So it's got a DEF pump off to the side. ECU controlled injection, just like any other fuel injection system. 1 gallon urea, or actually wouldn't be fuel, it'd be DEF, but yeah, it's the same idea. 1 gallon of urea treats about 100 gallons of diesel fuel. And this is used, they use the SCR system to allow them to tune the timing. So I added an EGR to the vehicle to reduce some emissions, but then I get a 2% decline in fuel economy by doing that. But by adding an SCR as well, I can either offset it completely, 2% to 5% increase in fuel economy, so I could even gain some fuel economy with that. So SCR allows return to normal injection timing, which is restoring the fuel mileage. And part of that, we have the SCR catalyst itself, the decomposition tube, the DEF injector, DEF pump tank and lines, NOx sensors, and the ammonia sensor. We're going to see why that's important in a minute. Here's an example of what the DEF injector would look like. You see how it's kind of just mounted in the exhaust there, and it just looks kind of like a normal top feed fuel injector. We got a little quick connect there, and a little 2-wire injector plug, and it's also heated and or cooled, I guess. There's also plumbing involved, right? So there's that quick connect, the other end of the quick connect there. So the tank, the lines, the pump, the coolant heater, electric heater itself, level sensor. So once again, in the cold weather, that needs to be heated. So we will do that because remember, it's 2/3 water, 1/3 urea. Now, NOx sensors are important with this because that'll determine the inlet and outlet NOx readings. And what does an SCR system do? Well, it reduces NOx in the exhaust. So it can be used in open or closed loop systems. Oftentimes there's like a little board there, and that has to be reset, relearned. One downfall, though, is it can mis-ID ammonia with NOx because it's the way it senses the NOx, it can sense excess ammonia in there. So if I have a problem with the urea injector, which is basically turning stuff into ammonia, it can misinterpret it and throw the computer off so it doesn't know what's going on, which is why some vehicles also have an ammonia sensor. So this one won't be fooled by other things in the exhaust gases, but it measures the ammonia levels after the SCR. So it can kind of be a check on the NOx sensor, allows much greater regulation of that. And like I said, it's immune to other exhaust gases. So how it kind of works, we have our inlet NOx, which is going to read the amount of NOx that's in the actual exhaust, and then the outlet NOx. After we inject the urea in there, so in this case, the DPF is first. You got the catalyst, you got the DPF collecting the soot, and then it injects the urea in there, and then my SCR is going to collect it, or is going to do the catalyzing. You also have a slip catalyst at the end. And theoretically, as long as everything's working the way it should be NOx should be much higher on that side than it is on that side, as long as everything's working right. But remember how I said NOx sensors can fail. NOx sensors can misidentify ammonia as NOx as well, so that could throw you off. So we actually have a special tool just for this. So if you work on diesel vehicles and you want to see if that SCR system's working properly, we actually have a system that will detect only NOx. That's all it does. It's a NOx sensor. If it gets the low performance, it'll derate, things of that nature. And like I said, it might not necessarily even notice it correctly. So there's this little handheld thing. It's like a little tailpipe sniffer. It's actually based on like our 5 gas, but it's a 1 gas. So it's just NOx. It's able to verify that my NOx sensors are working. So for example, if my NOx sensor, my front NOx sensor is at 400 parts per million, and my rear NOx sensor is at 40 parts per million, I guess and the NOx sensor agrees with this, then I guess it's okay. All good. It's working. It's reducing it by, that's only 10% of that. Reduce it by 90%. If it is reading 400 parts per million on the way in, 800 parts per million on the way out, and the NOx analyzer is just reading at 400 parts per million, well, we got a total failure there. SCR and slip catalysts are most likely the fault. If my front NOx sensor is reading at 150, my rear NOx sensor is reading at 300, and my analyzer is reading at 300, then that means my first NOx sensor has failed to the low side. If I'm reading 600 in, 400 out, and I'm only getting 10 out, well, that means that the SCR is working, but my NOx sensor on the backside, sensor 2, is failed high because it's reading too high. But actually analyzing the NOx coming out the back end, it's fine. If I have 400 in, 400 out, and I'm reading 400, then it's a DEF issue. It's probably not injecting it, or it's contaminated. And then if I have 400 going in and 400 coming out, but I'm reading 250, that means it's partially failed. Right. So once again, it can misidentify urea for NOx. So just because it's reading it on the back end, I'm reading what's truly in there. Now, once again, this is a guide. This isn't 100%, what you would necessarily use, but there is, be aware that there is a special tool for that we do have. You could do it with a 5 gas too and just read the NOx. But one of our industrial DSDs actually came up with that idea and helped develop it. So kudos to him. Speaking of after treatment and problems and things like that, this actually came from our customer care department. I was sitting in on some every Wednesday. We have about an hour where we listen into customer care calls live. They just answer them and we just listen to what's going on the call. And this we heard one time, and it's fairly common apparently. If you have a P242F, you might not be able to do a regen. It may not allow you to do a regen, and you might think that the computers or the scanner's not working properly, which is not exactly what's going on. It is that we have an issue with the code. So this basically means that the exhaust filter is full, power reduced C dealers. So in that case, it's plugged. The DPF is plugged, and you most likely need to replace it. Possible causes here: progressive damage to the after treatment system from an engine failure, including but not limited to excessive fuel, oil, or coolant in the after treatment system, may contribute to high pressure related fault. The DPF could be plugged. Operating in light load conditions that prevent exhaust temperatures from being high enough. Now, I will say the customer is going to get plenty of warning of this because they'll keep getting the things on the dash say, hey, you need to do a regen, you need to do a regen, and finally it goes into derate and it throws his code. So in order to do that, we need to go in with the tool and do what we call a stationary desoot. You could do this anytime. It's just kind of just a stationary parked regen. But they call it a desoot. That's another thing that people get confused with too. They don't know where it is in the tool because they don't see regen. All right. So stationary desoot. Initiates a stationary desoot. The stationary desoot procedure requires up to 80 minutes to complete, plus the warm-up time needed before the desoot begins. Refer to service information. Vehicle needs to be in park, parking brake engaged, vehicle operating temperature, vehicle not moving, and fuel level greater than 4 gallons. That's important. If you only got 2 or 3 gallons, it's almost on E, then you're not going to be able to do it. Because remember, it injects diesel fuel into the exhaust to do that. Correct any active DTCs not related to desoot. Stationary desoot will be aborted if any of the enable conditions are no longer met during this course of the procedure, including fuel level, including that P242F. Vehicle must be parked on a non-flammable surface. The spare tire must be lowered, and a 12-foot perimeter must be established around the rear of the vehicle because the tailpipe is going to get hot. Remember, the exhaust gases will be about over 1,000 degrees. And you go through, and then it will go through the procedure. There's also a DPF replacement, so if I can't do a desoot on it and it's clogged and I need to replace it, well, I can go in here and do a DPF replacement. So what that does is it resets the soot load estimate values whenever the DPF has been replaced. The engine can't be running to do this. Go in there, and then it'll just reset. It's a simple wait 10 seconds, and it resets it. Cycle the ignition off for 10 seconds, and you're good to go. Let's look at some other stuff that's in there on the tool. Because there's a lot of good stuff in the tool. So let's see. First one is the RAM. So we were just looking at that. Okay, it's behind security, of course. All right, so let's go into engine. See what we can see. Functional tests. Let's see. What would be diesel specific? Lift pump, I guess. Yeah, pretty much it. Diesel specific anyways. You're going to see some of these tests with gasoline engines too. After treatment system, deferductant, fuel pressure override, fuel system run-up test, variable geometry turbocharger, sector gear hysteresis test. That's a mouthful. Injector kill test. That's useful for seeing misfires because remember, there's no spark, just fuel. If we kill the fuel and doesn't run any worse, then we know that injector is probably bad. High pressure fuel system test for the high pressure fuel system. Then miscellaneous functions, DPF replacement we just saw, stationary desoot we just saw. Let's see. Idle shutdown timer, because of the diesel idle, you can change the length of the timer. Reset injector compensation value, so that would be like the injector quantity adjustment on the Ford. So you'd have to do that when you replace injectors. All right, and then let's just look down here really quick. Dosing control units down here as well. So there's some miscellaneous functions in there. Actually, that's just ECU information. And the codes will throw in the engine. That's what that's going to tell you. So it's listed separately, but you can get to it all through the there. And then variable geometry turbo as well. So that's just going to be ECU information. So let's look at guided component tests as well. Engine, and let's see. So what would be relevant to all the stuff we talked about? DEF systems. So we got the injector pump, the injector, the line heater, tests for those. Let's see. Exhaust gas temperature sensors, exhaust pressure differential sensors, exhaust pressure sensors, fuel heater, in the fuel system, the injector itself, fuel control actuator, all sorts of things there. Let's see. NOx sensor for sure. So you can go and you can do a voltage test. This actually runs over the CAN bus. Selective catalyst reduction module. It's going to give you the pinouts. Water and fuel sensor be important. All right, so all sorts of different tests that you can do in the guided component test as well. Next one, let's do the Ford. So on the Ford, we have in the engine, Functional tests, special functions. So DPF parameter reset, that's like a reset when you replace it. Power balance, that you can check the different as it's misfiring or if not misfiring and see whether or not it is misfiring. You can also turn the injectors on and off. So like this, you get a little graph, and then you can turn the injectors on and off, and then you'll see how they contribute. So that's helpful. Glow plug monitoring self-tests, injector electrical self-test, DPF dynamic regen, static regen, injector quantity adjustment we showed earlier, SCR, different system parameters, emptying, dosing, refilling, visual leak checks, and the like. So a lot of stuff there. You can see all the SCR stuff's integrated with the engine, and then let's just go down here and check real quick. Nothing related on that one. So that's all in one place. Then for guided component tests, we can see things like your EGR system, EGTs, exhaust pressures, reductant injector, reductant pump, reductant pressure line heater assembly, turbocharger actuator for the variable geometry turbocharger. There you go in there. That's just a pretty simple one, on and off. So lots there. Let's pull up a Chevy. So on our Duramax, in there we got functional tests, DPF tests. So regen enable, service regen, pressure sensor reset, catalyst reset. Reductant system malfunction warning service bay test. So as a service bay test you can do on the reductant system. So that's the SCR system. Cylinder power balance again. Output controls, NOx sensor reset in there. Reductant injector, tank level reset, catalyst reductant load and reset. All sorts of resets in output controls, just so you know that's where they put them. Now let's see if this one has a separate glow plug control module in there. And then if we go into guided component tests, same type of thing. So def injectors, purge solenoid, hydrocarbon injector, NOx sensor. That's pretty much it. Exhaust pressure sensor, exhaust temp sensor. There again, turbo vane position sensor. All that stuff. Position solenoid. All basically diesel specific. And then lastly, we'll do the Sprinter. So those are everywhere, all over the world. Actually, I wanted to pull up the 19 Sprinter, actually. Let's see, do this, do this, do this. There we go. Okay, so we'll go in here. Sprinter. All right, so in the engine here, we're going to have special functions, adaptations. So there's going to be a few things in there, like the process after replacement of the DPF pressure sensor, after oxygen sensor upstream of CAT, after replacement of oxidation catalytic converter. Let's see, teaching to use DPF. Reset learn values of NOx sensors. So if you replace the NOx sensors on this vehicle, you need to relearn them. After replacement of SCR. So definitely a lot of different things. And there's a regen right there while driving. Replacement of AdBlue metering valve. So there's a couple AdBlue things in here. Output controls. Diagnostic glowing. Cylinder deactivation. EGR. Injector programming, once again. Got to go in and code those injectors. And then on this one, this confuses people too because they don't know where to find the AdBlue system. They call it AdBlue as a selective catalyst reduction because it's got the blue DEF fluid, right? So AdBlue is in there. And I just got to pick the right variant. And functional tests, it's going to be resetting calculated fill level, AdBlue return, visual leak test, dynamic test of AdBlue delivery pump. Actuator tests in there, a couple different metering valves and heating tank heating elements and stuff like that. And then if we go over to guided component test here, you can see temp sensors, pressure sensors, water and fuel sensor, glow plug module, Go to the fuel system. You're going to get your fuel injectors, fuel quantity adjustment valves, fuel temp sensors, high pressure fuel pump, charge temperature sensor, DPF differential pressure sensor, DPS. That's going to tell you all about it. So a wealth of information within the scan tool. Like I said, this is mainly North America. In Europe, it's going to be the same type of deal because they're actually bigger on diesels in Europe. Not sure if you know that. If you're from North America, you may not be aware of that. But yeah, big diesel over there. But they're small diesels, right? So big diesel, but small diesels. So a lot of 4-cylinder diesels, things like that. Most vehicles have a diesel option over there. So once again, our scan tool covers a lot of those as well. So rest assured, if you're working on diesel vehicles, hopefully we've demystified a little bit about it if you don't work on diesel vehicles. And hopefully you can rest assured that if you have a Snap-on scan tool, you'll definitely be able to cover a large swath of the diesel stuff that's out there. And with that, that's our time here today. So make sure you tune in for new diagnostic content every week. We'll be premiering a new video every Wednesday at 7 p.m. UK time, so make sure to check it out here on our YouTube channel. Please make sure you also subscribe, thumbs up, and ring that little notification bell so you'll know anytime we post new content. With that, time for questions. Now, if you have any questions, once again, if you're watching this on the premiere, just leave it in the live chat and we'll do our best to answer those. Otherwise, leave a comment under the video and we'll get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've been giving you today. Hopefully we'll see you next week, and we'll see you on any of our other videos. Have a good week, have a good night, and take care.